So in section 4.5, this is all about optimization. So what we're going to try to do is figure out some way to maximize or minimize something. So we might want to minimize the cost if we're producing things. We want to maximize the profit, or we could maximize the area or minimize the amount of fencing needed for something. So all of these are word problems, right? So here's kind of some 6 basic steps to think about. First and foremost, read the problem. Okay? Read it several times if you have to. So make sure that you know what you're looking for. Identify what you need to maximize or minimize. Make sure you know what all the unknowns are, anything that's given to you, and what conditions might apply. The second thing I do is absolutely draw a picture. Okay? Draw a diagram of it. Now, especially when that comes to geometric shapes and things like that, or if you have graphs that are involved. But draw a picture if you can, because it does help. Assign all the variables to anything that you don't know. Okay, so if you need to find length or width, you have L or W for lengths and widths, whatever it is. Okay. Then come up with some kind of equations that relate all the variables. Now, you might come up with a whole bunch of equations, and you may not need all of them. That's okay. But just any way that you can relate the different variables together, jot that down. All right. So, if you have the equation that you want to optimize, say you're trying to maximize the area of something, and that area formula contains more than one variable. The number 5, it's not quite. If the equation that you want to optimize if that has more than one variable, then you want to take any of the other equations that you came up with and try to come up with a way to use those to substitute into the one that you're optimizing, and so you only have one variable left. And then you're going to find the derivatives, set them equal to 0 to see where you have maxes and mins. If it's closed interval stuff, remember you have to test the endpoints as well, because you want absolute max and min, not just the local ones. All right, so that's kind of a lot to remember. So let's just run through some examples. So the first one, nice, simple, straightforward. We have a farmer. There's 2,400 feet of fencing, and he wants to fence off a rectangular field that borders a straight river. He needs no fencing along the river. So what are the dimensions of the field that has the largest area? Okay, so first off, largest area, and it's a rectangular field, and it borders a river, right? So here's my river. We got some water running around in there, and we're going to put up a fence, and I don't need fencing on that side, so I've just got this. Okay, so there's my fence, and he's going to have like little horses in there or something. Okay. Little tail hanging down and a little mane. So how do you like my horse? There you go. So how do you find the area for a rectangle? So jot down, I know the area is the length times the width, so I'm just going to say L times W. Now, what else do we know? We know that there's 2,400 feet of fencing. So imagine what I'm doing is if I roll out the fence and I go all the way around the edge, that's 2,400 feet, right? So if I start labeling my diagram, there's an L there, there's the width, and there's another length, or however you want to assign those variables. So if I add all of those sides up, that should total up to 2,400. And then it says, of course, what are the dimensions of the field? So that's what I need to eventually answer. what the dimensions are for that rectangular pen with the maximum area. So I need to maximize the area, so that's the one I'm going to optimize, and I have two variables in it, an L and a W. I would like to narrow that down, so what I'm going to do is take this second equation, and I'm just going to go ahead and solve it for W. So that's 2400 minus 2L. And then if I make that substitution and take this and put it in for the W there, that means I'm going to have the area is L times 2400 minus 2L. So just simplifying that a little bit. Now I've got that equation that I'm trying to optimize down to one variable, so now I'm going to use the techniques that we'd used in prior stuff to do that. So look at the derivative. That's going to be 2400 minus 4L. I want to set that equal to 0. And then we can solve that. See, 2400 divided by 4, right? So that'd be 600. So the length of the field is 600 feet. Now I need to find out what the width is, right? So I could go back up in that other equation that I had and just substitute that in to find out what the width is. And that would be, what, 1200? So the length is 600 feet and the width is 1200 feet. Now, it didn't ask me what the area was, so I really don't care if I answer that or not. It just said what are the dimensions of the field. If it had asked for what the maximum area is, then I would take the 1200 times the 600 and come up with 720,000 square feet. Okay, but didn't need to do that on this particular question. All right, so let's move on to a couple other ones. What's the maximum vertical distance between the line y plus 2 and the parabola y equals x squared for x between -1 and 2? So I think the first thing I'll do is sketch the graphs of those things. Because I gotta have a picture of what's going on, because otherwise it's kind of hard to make sense of this one. So we have a line, x plus 2, and that would be this thing. And then we have this parabola, y equals x squared. And we want to know what the maximum vertical distance is. So vertical distance, we're looking at the distance between things right here and here. And I want to know where that's the biggest. So, I mean, think about moving this line over. Clearly, it's not like up in this little corner here or way over in this corner. You know, it's somewhere here in the middle. But how would you find that distance? So if you imagine those points, all you're doing, if you want the distance between here and here, then you just subtract the y coordinates, right? So the distance I'm looking for is just the y coordinates. Now, it's the top one is from the line, okay, and the bottom one's from the parabola. Now, the y coordinate for the line, you find that by doing x plus 2, correct? Minus, and then the y coordinate for the bottom one is given by x squared. Hey, so I have, that's the equation I want to optimize, and it's already got one variable, so I don't need any other kind of equations running around. Um, so, whoa. So let's just find our derivative, and I'm going to call that d instead of distance, okay? So d is negative x squared plus x plus 2. So the derivative, negative 2x plus 1. And if we set that equal to 0, we're going to come up with x equals 1/2. So that's where this thing occurs. It doesn't tell me what the distance is yet. I would have to go back and substitute that into my distance equation and say, okay, well, that's 1/2 squared plus 1/2 plus 2. Plus 0.5 plus 2. And I'm coming up with that distance being 2.25. See, without drawing the graphs on that, I'd have not known which equation to subtract from which, things like that. That's why I've usually got to have a picture. Now, this part, where it's between -1 and 2, is important because, well, clearly on the graph, that's this part where they intersect. But if you went further out, of course, there would be larger distances. I mean, if I tried to do it from out here, maybe I could find something that's larger, and of course, it goes up to infinity. Okay. So we kind of want to bound ourselves where we have that minimum in there, or maximum. All right, let's see what else we got going on. So consider the following problem. We've got a box with an open top, and it's to be constructed from a square piece of cardboard 3 feet wide by cutting a square out from each of the 4 corners, bending up the sides, and finding the largest volume that the box can have. All right. So you're going to have to imagine this. Now, if you want, and this is exactly what I do, and I would do it in class if we were actually in there. You got a big square piece of cardboard, okay? And this thing is 3 feet wide on each side. And then what we're doing is we take each corner and we cut a square out of that corner. Okay, and then we're going to fold up the sides. Now, grab a piece of paper and do this. Just tear the corners off, fold up the sides, and see what happens. Okay? So I don't know what size square that is, so I'm going to call each side of that x. Okay. Now, let's see. I want to find the largest volume. So how do you find the volume of the box? A volume is a length times a width times a height. Okay? Now, imagine this box. Now we've cut the corners out and we've folded up the sides. Okay. What is the length, the width, and the height of that? Okay. So remember what you're doing. You're folding right along these little lines in here. Okay, because that's the edges that get folded up. Okay, think about origami directions or something like that. These interior lines here, that's where we fold. Oh, I gotta move that stupid cursor. Okay. So that's the lines that we fold along. So these are the sides of my boxes. This on the bottom here would be 3 minus 2 of those x's, right? Because we got one on each side. And that would be the same for here. We get 3 minus 2x as well. And then the height of the box would be that x. It's how big of the square we cut out of. So on my folded one, that would be 3 minus 2x, 3 minus 2x, and then this height would be x. Now, there are some limits on what x could be, all right? X has to be bigger than 0 because we're cutting something out. And in fact, how much could we cut out? Well, we could only get halfway into that square, right? Because you're cutting in from both sides. And if it's only 3 foot long, once you get halfway, that puts an upper limit on the size of the square you can cut out. So I know x is supposed to be between 0 and 1.5. So let's see. Back to my little volume then. That's going to be 3 minus 2x times 3 minus 2x times the height, right? Because this is, the length is this, the width is that side, and the height is the x. See, I'm really just kind of making the substitution in there. I'm just didn't explicitly write it out a whole lot. Now I'm going to find the derivative, but I think it's still going to be simpler just to multiply this stuff out. So we're going to have 9x, let's see, that's 6, 12 minus 12x squared plus 4x cubed. So we find our derivative. And then we need to set that equal to 0 and solve, right? So let's set that sucker equal to 0. And I'm going to go ahead and look, all of that's divisible by 3, so I'm going to factor that out. And let's see, 4 times 3 would be 12. What times what would be a positive 12 and add up to a negative 8. So I'm going to do some scratch work over here off to the side. So something times something has to equal 12. But then if I add them together, that has to be the negative 8. So negative 6 and negative 2 work out perfectly for that. Multiply those, you get a positive 12. Add those, you get your negative 8. So I'm going to factor this. We get 3 minus 6x minus 2x plus 4x squared. Can factor a 3 out. And then we can factor out a negative 2x. That'd be 1 minus 2x. Factor the 1 minus 2x out, we get 3 minus 2x. And so get 0 minus 2x, and the other factor 0 minus 0 equals 3 minus 2x. So let's see here, x is going to be 1/2, and then over here, x will be, what, 3/2. Negative 3 divided by negative 2, yes. All right, that's not going to work. Because if we cut out 1.5 inches, we've got rid of the entire box. Okay, so that was at the upper end of our limit. And this inequality up here, really, I should have put strictly less thans and stuff like that. Okay, so that we have to throw out. So x is going to be 1/2. And then, what did it ask? It asked find the largest volume. So I'm just going to go ahead and substitute back into the volume equation. It did not ask for the dimensions, so really don't much care. And that would be that squared times x. I'm writing that as squared just because I'm running out of room, right? So 3 minus 1 squared, times x, times a half. So that's 2 squared times 1/2. So that would be 2 cubic feet. Because you get 4 times a half would be 2. So the largest volume I could make is something with 2 cubic feet. Okay, and I got one more. I think this is the last one. Nope, I got two more. So during the summer months, Terry makes and sells necklaces on the beach. Last summer, he sold necklaces for $10 each. So let's see, that seems like it might be important. Necklaces are $10 each, and he averaged 20 per day. When he increased his price by $1, so he increased his price by $1, he found that the average decreased by 2 per day. Find the demand function, assuming that it's linear. If the material for each necklace cost Terry $6, what should the selling price be to maximize his profit? Okay, so the demand function is going to be at what price, how many is he going to sell, right? So we really actually have 2 points, and here's the thing, assuming that it's linear, okay? So we have, let's say our ordered pairs are going to be price and the number sold, or that would be our demand, right? How many do we need? So the first thing says when he sells them for 2, he sold $20 a day. But then he increased the price by $1, so now he's selling them for $11, and the average decreased by 2, so then that went down by 18. What's the equation of the line that passes through those 2 points? So of course slope is going to be 2 over 1, or 2. So my demand equation will have we're going to call the price P, and the number sold I'm going to call N, or my XY coordinates. So we're going to have N minus 20, Y minus the Y coordinate equals 2 times X minus the X coordinate. So N equals 2X. But wait a minute. I did miss a negative sign in here. Ha. That's going to be screwed up now because this should be a negative 2, right? Because 20 minus 18, 10 is minus 11 would have been a negative 1. So that has a negative 2, a negative 2x plus 20. So N equals negative 2x plus 40. So there is my demand equation. So if the material for the necklace cost Terry $6, what should the selling price be to maximize his profit? Okay, so the material for each one cost $6. Now profit is equal to, oh, wait a minute, I used P for price. So profits is equal to the price times the number sold, correct? All right, now, it's asking what the price should be to maximize it, so we don't know that. We want to maximize the profit. And so we have the 2 variables, P and N. If I kept my notation very good, I would be happy. I didn't call those X, I called those P. Okay. So I can substitute in because the number should be negative 2p plus 40. I could find the derivative here. So profit prime. Okay. If we multiply those out, it'll be easier for the derivative. 2p squared plus 40p, right? So that's negative 40, negative 4p plus 40. Set that equal to 0. So his price should be $10 in order to maximize that profit. So, and you can kind of actually think about this a little bit if you started playing around with the ordered pairs. If you increase the dollar, increase the price by $1 and it decreases by 2, you can think about that going backwards as well. If you started off at $10 and you sold 20, if you went to $9, well, you would sell 22 of those, right? But holy crap, wait a minute, I've screwed something up. I forgot something really, really important because you know what? I didn't underline it. I didn't think about it. The material is costing Terry $6. So I actually need to take that out of my profit, don't I? So let me back up to my profit equation because it's the price times the number sold minus the cost. And I did not put that in there. Okay. So let me erase this part. And I'm hoping some of you, if not all of you, actually caught that before I went too far on. So that's $6 each. So if I look at my profit then, I'm going to need a little bit more room. It's the price that I'm selling for times how many I sell. So that part was okay, but I got to subtract the cost, and it's the $6 for each one that I sell. So it's 6 times the number of them sold. All right, so this would be P times N minus the 6 times N. Now let me simplify it a bit. Negative 2p squared plus 40p plus 12p minus 240. Now I look at the derivative. Profit prime, negative 4p plus 52. Set that equal to 0. And p in this case is going to be 13. So I need to set my price at 13 in order to maximize my profit. I might be selling fewer, but I'm making a little bit more money, right? Given the cost it takes and things like that. So price being $13, maximizing my profit. So just to tell you, what made me stop before was I got that same answer that I was already kind of started with, right? That it was $10 and I would sell 20 of them. And just typically in a math problem, that doesn't happen. It's not impossible by any stretch of the imagination. But just because the way these problems are designed, that doesn't happen a lot. So that made me stop and think for just a second. And it kind of kicked in what happened. So anyway, $13 is the price point to maximize profit. All right, now one more, last one. Manufacturer's been selling 1,000 flat screen TVs a week at $450 each. A market survey indicates that for each $10 rebate offered to a buyer, the number of TVs sold will increase by 100. Find the demand function. Okay. How large a rebate should the company offer the buyer in order to maximize the revenue? If its weekly cost function is 68,000 plus 150x, how should the manufacturer set the price of the rebate in order to maximize the profit? So the demand function, again, we're looking at the prices and how many of them are being produced and stuff like that, right? Okay, so they started off selling 1,000 flat screen TVs at $450 each. Okay, so let me set this one up same way I did the other one, all right? So 450 each would be 1 point, and they sell 1,000 of them. Okay, and then the next thing, we say, okay, well, we offer a $10 rebate, so that's going to be, my next point would be 440, and the number of TVs will increase by 100, so that's going to put it up to 1,100. Now, the slope of this line, okay, change in y over change in x, right, is just 100 over negative 10. Okay, so it's, I've wrote 1,000, but it's really 100, so that'd be negative 10. Okay, so then the equation we're going to have is the number minus 1,000 equals negative 10, and then the price minus 450. Negative 10p, and then just because I'm out of room here, we're going to have 450 plus 1,000, so that would be plus 1,450. So there's our demand equation. How large a rebate should the company order to maximize its revenue? Now, it's not maximizing profit, just revenue. So how much is it bringing in? So the revenue is going to equal the number of them sold times the price. See, this is what I was doing in that last problem because I was not thinking about taking out the cost and stuff. So let me scroll down a little bit and say, well, for our revenue then, well, that doesn't look like much in R, but I shook my computer screen, so it went weird. So the revenue is the price times the number sold, or the demand. I don't know where this extra 5 came from there. Plus 1450p. So let's look at the derivative. So that's negative 20p plus 1450. Again, set that equal to 0. And then when we solve, 1450 divided by 20, 72.50. So the price is going to be 72.50. That's a heck of a discount. Okay, so I'm going to take just a second. I mean, that's a huge discount. So let me make sure I haven't screwed something up here. So our demand function, we had 1,000 flat screens at $450 each. A $10 rebate set the price at $440. the number of TV sold will increase by 1,100. And so if we do the demand function and it's linear, then n minus 1,000 is negative 10 times p minus the 450. Okay. Oh, shoot. See, that price just looked really low. $14.50. What's 10 times 450? How about 4,500? Okay, so right there, screwed it up. So 4,500. So let me go fix these. 4,500. 4,500. 4,500 P. 4,500. Now 500 divided by 20 would be 225. So 225 would be the price that we need. All right, so how large a rebate should the company offer? Well, 450 minus 225, that would be a, well, $225 rebate. Or you can think about it as a 50% one, right? Because that's half off. Okay. So now, if they want to maximize profit, what are they going to do? Well, the profit, you have to take the revenue minus the cost, right? Profit is the money brought in, revenue minus cost. So in this case, we already have an equation for revenue. And we've got to subtract the cost. 68,000 plus 150. And it used X. I used N. Okay. So now we still have to, you know what, let me rewrite this where it's got more space. Minus 50N. All right, so this problem, I'm not caring a whole lot for the way that it's worded because it doesn't define what X is. But when you're talking about cost of producing things, it's, you know, how much it costs to produce each item. So intuitively, we know X should be the number of items. However, I really would prefer, you know, things being kind of spelled out. But that's okay. We have to make that substitution again. Okay, so negative 10p squared plus 4,500p minus 68,000 plus 150 times what was in. It was negative 10p plus 4,500. Ooh, I need more space. I can't write this small. Did not plan this out very well, did I, folks? Minus 1,500p. And then 4,500 times 150. is 675,675,000. Now let me combine my like terms. We got 4,500 plus the other 1,500. So that's 6,000p. And then negative 68,000 plus what, 675,000. So 743,000. Now we're going to look at the derivative. So profit prime, negative 20p plus 6,000. Set that equal to 0. And we solve that, so 6,000 divided by 20 would be 300. So if we set the price to 300, we'll maximize our profit. If we just need to maximize revenue, that's where we give the big rebate. All right, so look, I left a mistake in here because sometimes being able to spot your mistakes is actually a fairly important thing. And when I got that price being 72 bucks, something was off because that was just way, way low. So that tells you to go back and look for some kind of mistake, okay? So being able to identify sometimes that is pretty darn important. So there you go. There's a good example of identifying when you screw something up. So I hope you all find this helpful. It turned out a little bit longer than I wanted, but I kind of wanted to make sure to get several different examples in here, so that way when you look at the homework, it's not too completely out of left field. So hope it helps, and holler at me if you need any help, okay?